Okay, so in this video, we're going to look at ions and ionic bonds. Have very different meaning, the two terms. First off, metal atoms lose electrons to form positive ions, and we call these cations. I once knew someone who used to remember this by saying cats are positive, whatever works. So Li, that's the chemical symbol of lithium. Electronic configuration 2, 1 to begin with. That outer electron has to go. Atoms always gain or lose electrons to get full outer shells. And there's the equation to show that. Now, lithium started with 3 electrons. That means it started with 3 protons. Having lost an electron, it now has only 2. Still 3 protons, positive. Now 2 electrons, negative. 1 more positive charge, Li is plus. Non-metal atoms, as you would expect, are the opposite of metal atoms. They gain electrons to form negative ions called anions. All the ions in anion makes me think negative. Fluorine, for example, F, starts with electronic configuration 2,7, gains an electron to get a full outer shell 2,8. To begin with, 9 electrons, 9 protons, no charge. Negatives and positive cancel. At the end, still 9 positive protons, but now 10 electrons. Negative overall. But the formation of ions is exactly what it says, nothing more than that. It's just making ions. It's not ionic bonding. Whole thing with ions is they have different numbers of protons and electrons. Now, why do metal atoms lose electrons and non-metal atoms gain them? Well, we know that elements in group 8 don't react with anything. They have a full outer shell of electrons, they're stable. Atoms of other elements in other groups become stable by getting that full outer shell. Now, atoms can either lose electrons or they can gain them. They can lose all the electrons in the outer shell or by gaining enough electrons to fill that shell. And everything always goes the simplest way, which is well worth remembering. Take sodium, for example, group 1 in my table. Electronic configuration to begin with 2,8,1. Electrons to be lost or gained, well, losing 1 to get electronic configuration 2,8 as we see, that's a lot simpler than gaining 7. Sodium atoms always lose 1 electron when sodium reacts. Same with magnesium in group 2. 2 in the outside shell, 2 are lost to give me that full, stable outer shell. Aluminium group 3, yeah, 3 in the outside shell, 3 are lost. Charge on the ion, Al3+. And if I look at those 3 elements, sodium, magnesium, aluminium, the ending IUM tells me it's a metal. Other metals, maybe potassium, vanadium, chromium, IUM tells me it's a metal. It's not always the case. Some of the metals have been with us for thousands of years. Iron, copper, silver, gold, their names are very ancient. They don't follow that rule. But IUM is a giveaway. It's a metal. Phosphorus, group 5. 5 electrons in the outside shell. Easier to gain 3 to get 8 than it would be to lose 5, so that the second shell became the outer. Phosphorus atoms always gain 3 electrons to become P3-. And if 3 electrons are gained, I've now got 8 in the outside shell. Sulfur in group 6, 6 in the outside shell will gain 2. 2 gained, my charge as 2-. Chlorine, 7 in the outside shell, only needs to gain 1 to give Cl-. So, metal atoms lose their outer electrons, atoms of non-metals gain them. So the atoms of a metal will, if they have enough energy, donate their outer electrons to the atoms of non-metallic elements. And when this happens, the atoms become charged. They are now called ions. Positively charged metal ions will now be attracted to negatively charged non-metal ions. Opposites always attract. Ionic compounds are formed when the electrons are transferred between a metal atom and a non-metal atom. They're transferred from the metal atom to the non-metal atom. The actual definition of an ionic bond is a bit different. It's the electrostatic attraction between oppositely charged ions. In other words, ionic bonds can be made once ions form. The ionic bonds can only form after electrons have been transferred. Yeah. Number of electrons gained or lost, as we've seen, depends on electronic configuration. And atoms gain or lose electrons to become ions. That simple rule always goes the simplest way. And my first example, a group 1 element. What do I know that means? 1 electron in the outside shell. A group 7 element, 7 electrons in the outside shell. Here's sodium as an example of a group 1 element. Those diagrams look very busy. Sodium with 1 electron in the outside shell, I see it there as a cross. Chlorine atom with 7 in the outside shell already, I can count. They're in pairs, 2, 4, 6, and 1 on its own, that's 7. 1 to be gained. My next diagram's easier to follow, I think. There's no need to draw the inner shells unless we're asked to. In this case, the outer sodium electron is transferred to the chlorine. Sodium becomes positively charged. It lost a negative electron. Chlorine becomes negative, and we call it chloride now. So we only need to draw the electrons in the outside shell. They are the ones that will be lost or gained. Thinking about that, all group 1 elements have 1 electron in the outer shell. My example is looking at sodium. I could have chosen any other group 1 metal. 1 electron in the outside shell, 1 will be transferred. Same with group 7. 7 in the outside shell, and I can say that about any of my group 7 elements. I could have chosen any. 1 electron will be gained to become a negative ion. Now, once that's happened, the exchange of electrons happened between, in this case, 1 sodium atom, 1 chlorine atom. But there are so many countless atoms doing this exchange. I don't just get single ions of both. And what happens there is every positive ion that's formed will be attracted to negative ions all around it. Same with the negative ions. If I look at the red, chloride ions are drawn in red. If I look at the red one in the middle of the front row, it is supposed to be 3D. I can see a positive blue sodium above and below. Positive blue sodiums to the left and the right. And it would be the same for every ion in that structure. If it makes it simpler, I've drawn 1 sodium ion beside the structure with red chloride ions above and below, to the left and the right, in front and behind. So each positive sodium ion now becomes surrounded by 6 negative chloride ions, and it's attracted to them all. In turn, each negative chloride ion becomes surrounded by 6 sodium ions. Now that forms what we call a lattice, and a lattice means a regular arrangement. In the diagram above, we've got positively charged sodium ions, negatively charged chloride ions in a regular pattern. Atoms of 1 charge become surrounded, ions of 1 charge become surrounded by many ions of the opposite charge, as many as possible. Now, ionic bonds are not the transferring of electrons. We've seen this already. They're the electrostatic attraction between oppositely charged ions. The electro part of electrostatic refers to electrons. They were the particles that were being exchanged. Static means that what gets made, that's the ions, they're not moving. My positive and negative ions attract each other and they're held in their place. Now that's a lot of ions. That means there's a lot of attractive forces. That causes sodium chloride to be a solid at room temperature. We could say high melting point. Sometimes confusing, we talk about volatility. A volatile substance is one that boils over easily. We also use the term in the English language to describe a volatile person, one who loses their temper and boils over easily. Well, because sodium chloride has a high melting point, we say it's got low volatility. I've got this regular arrangement of ions. That means the structure is always crystalline. When sodium chloride is heated strongly, high melting point, but strongly enough it will melt, and the liquid sodium chloride formed will conduct electricity because the ions are now free to move. Solid sodium chloride would never do that, will never conduct electricity, as the ions are held together in the lattice. And also because water is a polar solvent. That means that part of a water molecule has a slight positive charge, part has a slight negative charge. Ionic substances tend to be soluble in water. Sodium and chloride ions become surrounded by polar water molecules and become stabilized. The negative part of the water molecule would be attracted to the positive sodium ions. Positive part of the water molecule will be attracted to the negative chloride ions. Other metallic and non-metallic elements will also bond by forming ions. Next example, magnesium's in group 2 of the periodic table. Atoms need to lose the 2 outer electrons to get a full outer shell. Fluorine's in group 7. Fluorine atoms need to gain 1 electron to get that full outer shell. Now, if that's the case, each magnesium atom transfers an electron to fluorine atoms. Fluorine atoms will only accept 1, but if they do, they will now get full outer shells of 8. My magnesium atom can satisfy the 2 fluorines. And I've got my chemical formula I will highlight. MgF2. 1 magnesium, 2 fluorides. Quick question. State the chemical formula of magnesium chloride. Ooh. Now in our example, we looked at magnesium and fluorine. In the question, we're going to be looking at magnesium combining with chlorine. See how the name of the compound magnesium chloride gives away what's in there. Magnesium still in group 2. Chlorine, like fluorine, is in group 7. Chlorine atoms, like the fluorine atoms, needed to gain 1 electron. My formula will now be MgCl2. Atoms of elements in the same group behave in similar ways. And I see a 2-point question below. In what 2 states could magnesium chloride be expected to conduct electricity? Ions have to be free to move. And in that case, my ions are going to have to be liquid or dissolved in water in aqueous solution. That's 2 statements, 2 points. Other examples. Sodium, group 1. I look at the diagram below. Yeah, 1 electron in the outer shell. Oxygen, group 6. We just looked at oxygen, 6 in the outside shell drawn in blue. 2 sodium atoms would each lose their 1 outer electron to get a full stable shell. Oxygen started with 6, gained 2. The oxygen atom has now become a stable oxygen ion. And if I look at the number of atoms involved, 2 of the Na, sodium, 1 of the O, oxygen, Na2O. My most complicated example. Aluminium and oxygen. Going to form a compound, aluminium oxide. Aluminium in group 3. 3 electrons in the outside shell. Oxygen atoms again, group 6, 6 in the outside shell. So, aluminium atoms need to lose 3 electrons. Oxygen atoms need to gain only 2. So for my first aluminium on the top, I see 2 of its electrons are transferred immediately over to the first oxygen, but there's 1 left. I need a second oxygen atom to accept that additional electron. It needs another. Let it take it from the aluminium atom below. Now the central oxygen atom has 8 electrons. Stable. My last 2 electrons on aluminium would have to go to a third oxygen atom. I needed 2 aluminium atoms. I needed 3 oxygen atoms. That's why my chemical formula is Al2O3. General properties. They have high melting and boiling points. Good electrical conductivity, but only when the ions can move. Only when in aqueous solution or when they're molten. I get that regular arrangement of alternating positive and negative ions. That forms the lattice. That's here, the giant lattice. They're crystalline because of that regular arrangement. Brittle, I shall explain why. The ions arrange themselves into that lattice. In the diagram before, we had positively charged sodium ions, negatively charged chloride ions in that regular pattern. Ions of one charge become surrounded by many ions of the opposite charge. And that is what causes the properties of ionic compounds. Bonding causes properties. Once more, ionic bonds are not transferring of electrons. They are electrostatic attraction between oppositely charged ions. The ions have to form before we can get ionic bonds. Electrostatic, electro means charge, electrons. Static, they're not moving. Positive and negative ions are attracted to each other. High melting points because there's lots of attractive forces between ions of opposite charge. You could say low volatility. Regular arrangement of ions means the structure is always crystalline. Now, if the crystal structure is struck, a whole layer of ions can slide across. And if I look at my little diagram below, plus and minus to show positive and negative ions, ordered so that the positives are surrounded by negatives, the negatives are surrounded by positive, but just a gentle tap will cause a layer of ions to move. Now I have positive opposite positive, negative opposite negative. Repel. The crystal breaks. That makes the crystal brittle. They have to be heated strongly to make them melt, but when they melt, the liquid they form will conduct electricity because the ions are now free to move. Sometimes we say mobile. They will dissolve in water. Question 2. I'm given the information on element X, 1 outer electron. Element Y has 6 outer electrons. Which statement is correct? Take your time, pause the video. And my answer for this, if A has 1 outer electron, it tells me atoms of A have 1 electron to lose. They're actually in group 1, metal. Y has 6 outer electrons. 2 electrons to be gained. So my bonding will be ionic. Option A talks about a covalent compound. Nope. Option B, combine to make a solid compound, which I like because ionic compounds are solids, large melting points. And it will conduct electricity as a solid and a liquid. Oh dear, no. As a liquid, yeah. When molten, the compound formed would conduct electricity. But when solid, no. Ions cannot move. Elements A and Y can conduct electricity. Well, metals can. A is a metal. A, yes. Y is a non-metal. No. Last chance. A and Y combine to form a crystalline compound. We know it will be ionic. Atoms of A lose electrons. Atoms of Y gain them. That being the case, ionic, yes, it will form a crystalline compound, and ionic compounds have high melting points. Second question. Which statement describes the bonding in potassium fluoride? Potassium IUM is a metal, will form a positive ion. Fluoride comes from fluorine, non-metal, will form a negative ion. So my bonding has to be ionic. A is gone. B. Regular arrangement of molecules. Well, that term molecules we reserve for covalent. It contains ions. Option C, I like it. Surrounded by ions of opposite charge. Yes, that's what's building the lattice. And D. No, it's ionic. It will be a solid at room temperature. Next video I make will be on covalent bonding.